good morning and welcome. My dear students, this video is the first in the series of videos on econometrics 2. This is a new playlist that I'm going to upload for my students. So in this particular video, I will discuss how to specify a model and how to use some diagnostic tests for model specification or model mis-specification. So let me remind you that one of the assumptions of the classical linear regression model is that the regression model is correctly specified. So it means that the model should be correctly specified, it should not be misspecified. If the model is not correctly specified, we may be committing a specification error or model specification bias. In this lecture, we would look at this assumption, that is the specification of the model, because searching for an ideal model is like searching for something which is ideal. And usually in econometrics, students and researchers are looking for the best model, which is improvement or other alternatives. Particularly, we will examine some of the questions regarding this, and these include, for example, that what are the criteria in choosing a better model for empirical analysis. There may be a number of models that we may estimate, and we may be looking for a better model which is an improvement or alternative models. The next question that we would like to address is what types of model specification errors is one likely to encounter in practice. So we'll be discussing various model specification errors. And number three, what are the consequences if the model is misspecified? If you are committing specification bias, what would be the consequences? And number four, how can we detect specification errors? In other words, what are some of the diagnostic tools that we may use to diagnose specification bias in the empirical model? After detecting specification errors, what remedies can one adapt to rectify or to come up with a good model? And finally, we may also evaluate the performance of the competing models, and we may decide which of these models is improvement over the other alternative models. So we will try to come up with answers to these questions. So we start with the model selection criteria, and we are going to discuss what are the criteria that our chosen empirical model should satisfy. So the first one is that the predictions made from the empirical model must be logically possible and acceptable. So they must be based on logic. The second criteria is that our results or the model should be consistent with theory. That is, the results must be in line with the theory, and it should not refute any economic theory. The third criteria that we must keep in mind is that the explanative variable or the regressors must be uncorrelated with the error term. That is, there should be no endogeneity issue in the chosen model for empirical analysis. The fourth criteria that we may keep in mind is that of parameter constancy, which means the values of the parameters should be stable, otherwise forecasting will be difficult. Another criteria is that of data coherency, and it means that the residuals estimated from the model must be purely random or white noise. In other words, if the regression model is adequate or a better one, the residuals from this model must be white noise. It must be encompassing, which means that if there are a number of models, other models cannot be an improvement over the chosen model for empirical analysis. That is, the model that we think is adequate should be an improvement over other alternative models. Others should not be improvement on the one that we chose for empirical analysis. After this, we will discuss various types of specification errors, and there are a number of specification errors. So we would start with the, let us suppose On the basis of the model selection criteria, we have in mind the following model, which is uh, a cost function, and that is cubic total cost function, in which output appears as linear, quadratic, and cubic. In this model, y is the total cost of production, x is output. This equation is the example of cubic total cost function because the highest power of xi is 3r cube. So this is cubic total cost function. But suppose for some reason you use the following model, which is not cubic but it is quadratic, like this. Here x appears as a square, that is the highest power of the x variable is 2. Since model 1 or equation 1 is assumed to be true, and if you adapt equation 2, then it would constitute a specification error, and that means that we are omitting an important variable xiq. So this kind of specification error is known as omission of a relevant variable. Therefore, the error term u to I in equation number 2 is equal to u to I is equal to u1I plus b4 x1 to the power 3. Now suppose that another student or another researcher uses another model, and that is that the highest power of xi variable is 4 rather than 3. So we know that if equation number 1 is true, that is the cubic total cost function is true, but we use equation number 4, then it also constitutes a specification error, and this error is known as inclusion of unnecessary or irrelevant variable, in the sense that in the true model lambda 5 is equal to b0. So if we include xi square in the model, where the true model has only xi3 x1 square and xi, but we include also xi square, xi raised to the power 4, then we are also committing specification bias or specification errors, and that specification error consists in including an irrelevant variable, and that irrelevant variable is xi raised to the power 4. The new error term is in fact u3i is equal to u1i minus lambda 5 xi to the power 4 is equal to u1i, since lambda 5 is equal to 0 in the true model. Now assume that yet another researcher estimates the following model, and here instead of linear y we use natural log of yi, and rest of the model is the same as equation number 1 in the previous slide. In relation to the true model, equation 6 also constitutes a specification bias, and this bias is in the use of wrong function form. Here we are using wrong functional form. So if you use wrong functional form instead of the correct function form, we are also committing a specification error. In equation 1, y appears linearly, whereas in equation 6 it appears log linearly. So using log y instead of linear y, we are committing a specification error that is known as wrong function form. Finally, consider another researcher who uses the following model, where instead of actual yi we use some proxy of yi, which is yi star. Then we have beta 1 star, beta 2 star, x1 star, beta 3 star, xi square star, and beta 4 star, xi raised to the power 3 star plus u1 star. Now the equation number 7 is also not correct, because here yi star is equal to yi plus epsilon I, and xi star is equal to xi plus wi, where epsilon I and wi are the errors of measurement. So in this case, If you use proxy instead of y and x variables, then we are committing error of measurement, and this is also known as the specification error in the model. Equation 7 states that instead of using the true yi and xi, we are using their proxies. So that is not correct, and that may contain errors of measurement. So that is also one of the types of specification errors. Therefore, in equation 7, we commit the errors of measurement bias. Another type of specification error relates to the way the stochastic error term enters the regression model. So what does it mean? It means, consider for example the following bivariate regression model without the intercept term, where yi is equal to beta times xi times ui. So this is equation number 8, where the stochastic error term enters multiplicatively rather than additively, with the property that natural log of ui satisfies all the assumption of the classical linear regression model against the following model, which where the model is yi is equal to axi plus ui, where the error term enters additively. So a question is, which one is correct? Although the variables are the same in the two models, we have denoted the slope coefficient in equation 8 by beta and the slope coefficient in equation 9 by alpha. Now if 8 is the correct or true model, would the estimate alpha provide an unbiased estimate of the true beta? That is, will expected value of alpha hat be equal to beta? If that is not the case, improper stochastic specification of the error term will constitute another source of specification error. So we must be pretty sure in what way we may use the error term in the model. To sum up, in developing an empirical model, one is likely to commit one or more of the following specification errors. So it means the researchers may commit one or more of the following specification errors. So what are these? That is, we may either be committing omission of a relevant variable or variables, or we may be committing error of including an unnecessary or irrelevant variable or variables, or we may be using wrong function form of the model, or there may be errors of measurement in the variable, or there may be incorrect specification of the random error term. But before turning to an examination of these specification, it may be better to differentiate between model specification errors and model mis-specification errors. So in the next slide, we will explain this. The first four types of the error discussed above, which means omission of a relevant variable, inclusion of an unnecessary variable or variables, adapting the wrong function form, or errors of measurement, they are known as model specification errors. So the first four types of error discussed are known as the model specification errors, in what we have in mind a true model, but somehow we do not estimate the correct model. In model mis-specification errors, we do not know what the true model is to begin with. In this context, one may recall the controversy between the Keynesian and the monetarists. The monetarists give primacy to money and in explaining changes in GDP, whereas the Keynesians stress the role of government expenditure to explain changes in GDP. So these are two different theories. So to speak, they are two competing models, and we must know which one we may use. Now we will discuss consequences of the model specification errors, and we start with the underfitting of a model, or when we are omitting a relevant variable from the empirical model that we are using for analysis. Suppose the true model is this, that is yi is equal to beta 1 plus beta 2 x2i plus beta 3 x3i plus ui. But for some reason, we use this model in which there is no x3, that is yi is equal to alpha 1 plus alpha 2 x2i plus vi. The consequence of omitting variable x3 are as follows. If an important relevant variable is left out or omitted, that is x3 is omitted, but this variable is correlated with the included variable x2, that is the correlation coefficient between x2 and x3 is not equal to 0, that is alpha 1 hat and alpha 2 hat are biased as well as inconsistent. So it means when we are omitting a relevant variable from the model, then the underfitting model, the two coefficients, the regression coefficients alpha 1 hat and alpha 2 hat are not only biased but they are inconsistent. That is, the estimated value of alpha 1 hat does not equal beta 1 and estimated value of alpha 2 hat is not equal to beta 2, and the bias does not appear as the sample size gets larger, and the variances of these estimators are also inconsistent. Even if x2 and x3 are not correlated, that is, if the correlation coefficient between x2 and x3 is equal to 0, alpha 1 hat is still biased, although alpha 2 hat is now unbiased. The third consequence is that the disturbance term variance, that is sigma square, is incorrectly estimated. The conventionally measured variance of alpha 2 hat is sigma square divided by summation x2i x square, is a biased estimator of the variance of the true estimator beta hat 2. Number 5. As a consequence, the usual confidence interval and hypothesis testing procedures are likely to give misleading conclusions about the statistical significance of the estimated parameter. That is, if we are omitting a relevant variable, then the convention confidence interval and the hypothesis testing procedures are likely to give us misleading conclusions and results. Number 6. There is another consequence, and that is that the forecasts based on the incorrect model and the forecast confidence intervals will be unreliable. We may not rely on the forecast based on the incorrect model. So the conclusion is, once a model is formulated on the basis of the relevant theory or the criteria, one is not advised to drop a variable from such a model. So we must use the true model that we have in mind, and we shouldn't drop a relevant variable. We shouldn't omit a relevant variable from this model, otherwise our results will be not reliable. Let us now consider the case of a model in which we use a irrelevant variable and we are overfitting a model. So we now suppose that yi equals beta 1 plus beta 2 x2i plus ui is the true model, but instead of using this model, we fit the following model where we have another variable in this model, that is x3i. Now in this case, we commit a specification error of including an irrelevant variable in the model. In this case, x3i is irrelevant if A3 is the correct model. Now what will be the consequences of this specification error? The first consequence of the committing overfitting model is that the OLS estimators of the parameters of the incorrect model are all unbiased and consistent, that is, estimated value of alpha 1 is equal to beta 1 and estimated value of alpha 2 hat is equal to beta 2, and estimated value of alpha 3 hat is equal to beta 3 is equal to 0. The error variance sigma square is correctly specified and estimated. the usual confidence interval and hypothesis testing procedures remain valid. So if these things are okay, that is the estimators are unbiased and the error variance is correctly specified, then what is the problem? The problem is that the estimated alphas will be generally inefficient. That is, their variances will not be minimum. They will be generally larger than those of the betas of the true model. So, even if the estimators are unbiased and the confidence intervals are okay and the error variance is correctly estimated, still there is a problem or a consequence with the overfitting of a model, and that is that the estimators are not efficient. Their errors are, their variances are not minimum, so they are inefficient, and their variances are generally larger than those of the estimators of the true model, that is the A3. So the estimators used in A4 model are inefficient as compared to the estimators used in the true model given in A3. The proofs of some of these statements can be found in your textbook, that is Gujarati, in Appendix 13A, Section 13A.2. So what are the various tests of model specification errors? The first one to use to detect the presence of irrelevant variables. Now let us assume that we have k variable model to explain a particular phenomena, and that model is yi is based on variables x2i up to xki. There are k variables in this model. However, we are not perfectly sure whether variable xk really needs to be included in this model or not. So one simple way to find out this is to test the significance of the estimated beta k with the usual t-test, and if the t-test is insignificant, then we may think that this variable is unnecessary to be included in this model. But suppose that we are not sure whether x3 and x4 really belong in the model. This can be easily done by f-test. Therefore, detecting the presence of an irrelevant variable or variables is not a difficult task. We may either use individual t-test or the f-test. It is, however, very important to remember that in carrying out these tests of significance, we have a specific model in mind. We accept that model as the maintained hypothesis or the true model. Given that model, then we can find out whether one or more regressions are really relevant by the usual T and F test or not. But we should note it carefully that we should not use the T and F tests to build a model iteratively. That is, we should not say that initially y is related to x2 only because beta 2 hat is statistically significant, and then expand the model to include x3 and decide to keep that variable in the model if beta 3 hat turns out to be statistically significant, and so on. This strategy of building model is called the bottom-up approach, or by somewhat pejorative term. So the primary objective of data mining is to develop the best model after several diagnostic tests, so that the model finally chosen is a good model in the sense that all the estimated coefficients have the right algebraic sign and they are statistically significant on the basis of T and F test, and the R square value is reasonably high, and the Durbin-Watson D test statistic has acceptable value around about 2. The pursuit in the profession look down on the practice of data mining. That is, we shouldn't use data mining. There are some other tests which are used for omitted variables and incorrect functional form. In practice, we are not sure that the model adapted for empirical testing is the true model, the whole truth, and nothing but the truth. On the basis of theory or a prior empirical work, we develop a model that we believe captures the essence of the subject under study. So it means that we must get guidance from the theory or the previous empirical work that other researcher has done. We then subject the model to empirical testing. After we obtain the results, we begin the postmortem, keeping in mind the criteria of a good model. It is at this stage that we come to know if the chosen model is adequate or not. In determining model adequacy, we look at the broad features of the results such as the adjusted R-square value, the estimated t-ratios, the signs of the estimated coefficients in relation to their prior expectation, the Durbin-Watson d-statistic, and so on. If these diagnostics are reasonably good, we may claim that the chosen model is fair enough representation of the true situation. If the results do not look encouraging because the adjusted R-square value is too low, because very few coefficients are statistically significant or have incorrect sign, or because the Durbin-Watson d is too low, then we begin to worry about the model adequacy and look for remedies. Maybe we have omitted an important variable, or have used wrong functional form, or haven't first differenced the time series, and so on. Now we are examining the estimated residuals. Examination of the residual is a good visual diagnostic to detect autocorrelation or heteroscedasticity in the estimated model. But these residual can also be examined, especially in cross-section data, for the model specification errors such as omission of an important variable or incorrect function form. If in fact there are such errors, a plot of the residuals will exhibit distinct patterns, some kind of patterns, systematic patterns. To illustrate, let us consider the cubic total cost of production function which we discussed earlier, and assume that the true model cost function is described as a cubic total cost function given by B1 equation, but a researcher fits the following quadratic function specified as equation B2. And another researcher fits the following linear equation. Although we know that both researchers have made specification errors, let us see how the estimated residuals look in these three different models. So let us see in the following figure, it speaks for itself. As we move from, so here, these are the residuals of the three different models. The first one is for the cubic, this one is for the linear, this one is for the quadratic model, and this one is for the cubic total cost of production function. And these are the estimated residuals from the linear, quadratic, and cubic total cost. There are 10 observations. So these are the estimated by I hat. These are the estimated by I hat for the quadratic, and these for the cubic cost. So let me explain this. As we move from the left to right, that is, as we approach the true model, not only are the residuals smaller, but also they do not exhibit a pronounced cyclical wins associated with the misfitted models. The utility of examining the residuals plot is thus clear. If there are specification errors, the residuals will exhibit noticeable patterns or systematic patterns. Durbin-Watson d-statistic, once again we examine. If we examine the routinely calculated Durbin-Watson d-statistics in table 13.1 in the book, we see that for the linear cost function, estimated d is equal to 0.716, which suggests that there is positive correlation in the estimated residuals. Likewise, we computed d value for the quadratic cost function that I explained in the earlier slide, and that is equal to 1.038, whereas the 5% critical value is DL 0.697, and upper limit is DU, that is equal to 1.641, indicating indecision. But if you use the modified D test, we can say that there is a positive correlation in the residuals for the computed D is less than the DU. For the cubic cost function, the true specific, which is the true specification, the estimated d value does not indicate any positive correlation in the residuals. And for that, the d is equal to 2.70. The observed positive correlation in the residuals when we fit the linear or quadratic model is not a measure of first order serial correlation but of model specification errors. So this is how we detect specification errors in the model. The observed correlation simply reflects that the fact that some variables that belong in the model are included in the error term and need to be pulled out from it and introduced in their own right as explanatory variables. If we exclude the xi3 from the cost function, then as equation 3 shows, the error term in the misspecified model equation 2 is in fact u1i plus beta 4xi3, and it will exhibit a systematic pattern, that is positive autocorrelation, if xi3 in fact affects y significantly. We may also use Ramsey reset test. Ramsey has proposed this test, which is known as a regression specification error test, abbreviated as reset. We illustrate this only by the simplest version of the test. Let us continue with our cost output example and assume that the cost function is linear in output as follows. That is, yi is equal to lambda 1 plus lambda 2 xi plus u3i, where y is the total cost, x is the output. Now, if we plot residuals ui hat obtained from this regression model against yi hat, the estimated yi from this model, we get the picture shown in this figure below. Although summation ui hat and summation ui hat times yi hat are necessarily zero, the residuals in this figure show a pattern in which their mean changes systematically with the yi hat. So this basically indicates the misspecification error. So this would suggest that if we introduce yi hat in some form as regressor in the above equation C1, it would increase R square, and if the R square increase statistically on the basis of F test, it would suggest that the linear cost function was misspecified. This is essentially the idea of Ramsey's reset test. And here is the steps involved in Ramsey reset test, which are as follows. From the chosen model, obtain the estimated yi, that is yi hat, then rerun the regression, introducing yi hat in some form of an additional regressors. From figure 13.2 that will be shown to you in the next slide, we observe that there is a curvilinear relationship between ui hat and yi hat, suggesting that one can introduce yi square and yi cube as additional regressor. Thus, we run the following regression in which we use yi hat square and yi hat cube, and let the r square obtained from the C2 equation be R2 new, and that obtained from C2 be the R square old. Then we can use the following F test. This is the formula, and if you look at these calculations, these statistics are based on these two models. Then finally the F test is equal to this, and it means that this is highly significant. So if this is highly significant, then what is the result? So we can verify that this F value is highly significant, and it indicates that the model is misspecified, that is the linear model is misspecified. Of course, we have reached the same conclusion on the basis of the visual examination of residuals as well as the Durbin-Watson D test values that we discussed earlier. One advantage of Ramsey reset test is that it is easy to apply, for it does not require one to specify what the alternative model is, but that is also its advantage, because knowing that a model is misspecified does not help us necessarily in choosing a better alternative. This is another test, that is the Lagrange multiplier test for adding variables. To examine this test, we will continue with the preceding example that we used already. And if we compare the linear cost function C1 with the cubic cost function C2, the former is the restricted version of the latter. The restricted regression assumes that the coefficient of the squared and cubed output term are equal to 0. To test this, the LM test proceeds as follows. Estimate the restricted regression by OLS and obtain the residuals UI hat. If in fact the unrestricted regression is the true regression, the residuals obtained in the restricted regression should be related to the squared and cubed output terms, that is xi square and xi cube. This suggests that we regress the UI hat obtained in step 1 on all the regressors, including those in the restricted regression, which in the present case means UI hat equal alpha 1 plus alpha 2 xi plus alpha 3 xi square plus alpha 4 xi square plus vi. So here we regress the estimated residuals, where V is an error term that has the usual properties of the classical linear regression model. For a large sample size, Angel has shown that n times the coefficient of determination estimated from the auxiliary regression given in D1 follows the chi-square distribution with degree of freedom equal to the number of restrictions imposed by the restricted regression. 2. In the present example, since the terms xi square and xi cube are dropped from the model. Symbolically, we write n times r square is asymptotically equal to chi-square with number of restrictions, where SE means asymptotically, that is in the large samples. So if the chi-square value obtained from equation D2 exceeds the critical chi-square value of the above chosen model level of significance, we reject the restricted regression. Otherwise, we accept the restricted regression. To illustrate this test, we will continue with the preceding examples. This is exactly the same, and here we actually have shared with you the results of the regression, the restricted regression. This is the results of the restricted regression, and these are the results from the regression of UI hat on all these variables, and this is the R square. Okay, so although our sample size is 10 and it is not large, just to illustrate the LM mechanism, we obtain nr square, and that is equal to 10 times 0.9896, that is equal to 9.896 from the chi-square table at the end of this book. For 2 degrees of freedom, the 1% critical chi-square value is about 9.21. Since the observed chi-square value is greater than the tabulated value, our conclusion would be to reject the restricted regression. So we reach the similar conclusion on the basis of Ramsey test as by the LM test, the Ramsey test, the T test, F test, and the Durbin-Watson D test. Thanks very much for watching this video. If you haven't yet subscribed to the channel, kindly subscribe to the channel, and don't forget to click on the bell icon so that you could get timely notification